Great. Okay, everybody. So I guess we'll get started for the day. Nice to see you all. Welcome back. Let's see. So in terms of announcements and all that good stuff, how many of us have run the starter code for the homework? Not all of you. That's suspicious. It's like a 5-minute job, and then if it's not a 5-minute job, then you're going to be glad that you tried the 5-minute job. So yeah, again, my strong suggestion is to get started with your homework simply by running the starter code. You don't even have to think about SVDs. You can just run the starter code. Because what I don't want is for you to discover it doesn't work on your computer at the last minute, right? That's all. Like this is just like computer graphics code is notoriously annoying to get to run on computers. It's a little bit better in 2023 than it was back in the day. But even so, like I prefer to know that now rather than later. As I put out an announcement, our usual colleague here has found a few technical mistakes around the corners of our homework. So those have been patched up. And then that actually got me thinking about this chapter of the book. And I decided I really should patch up the same mistakes in the textbook. So I also uploaded a slight revision to the chapter. So the old chapter actually was not wrong, but I tried to like go back and carefully add indices so that it's like very clear the size of every matrix that shows up in the chapter. In that process, every time I try to change some technical thing like that, probably I end up introducing 50 more typos. So I encourage you all to read that chapter very carefully and let me know if you spot any mistakes. All right, any procedural questions, comments, concerns before we get started with, math? Sorry, not math, computer science. I don't want to offend the mathematicians. I've already done that once today. Okay, right, so in that case, let's get started. So today, we're going to cover, you guessed it, another way to factorize a matrix. This is what we do for the first chunk of this course, is like 50 different ways to chop up a matrix. In fact, I think we do kind of the main pieces of the pantheon. There are other factorizations out there, but for the most part, they can be derived from the ones that we're doing in this course. Not all, there's some weird ones, but maybe we'll come back to that later. So today, we're going to introduce a new type of factorization. This is called QR factorization. Does anybody know why it's called QR? Yeah. Yeah, because we called the matrices Q and R, and whoever wrote it down the first time decided those were the letters, and now we're stuck with that. Yeah, so to my knowledge, there's no real pattern there. But in any event, the QR factorization is going to be particularly useful for non-square matrices, which is a thing that we have like not done carefully yet, right? Because so far our LU factorization, at least the way that we've derived it, really was for like invertible square stuff, right? And certainly Cholesky, right? Because remember that positive definite condition doesn't even make sense for non-square, okay? And really the application we're going to have in mind for QR factorization is least squares problems. Because again, those are like hella important. Cool? Cool. All right, so here's the basic issue. How did we do least squares before? Remember, we're going to write down the same formula that's motivated like the last 16 lectures of this course, which is ironic because we only had like 5. So like we solve the following optimization problem. I'm going to ask the same question I ask at the beginning of every lecture. This might make you think about the kind of thing that might show up on your midterm exam. Speaking of which, we should write a quiz. How should I solve for x here? What should I do? I'm literally dying because if you guys don't know the solution by now, or a solution, we're in a lot of trouble. Not Chris, you're the TA. The normal equations, thank you. Now somebody else, what is the normal equation? Yeah.
A transpose A
Like that. That's right. Right? And like so our basic point here was that if we know how to solve linear systems of equations, then secretly we actually know how to solve this problem here by constructing the matrix A transpose A and then solving the system, and then we get x, right? At least under the assumption that A transpose A is invertible, which is roughly equivalent, in fact exactly equivalent to the columns of this matrix being linearly independent. Okay? So that's our story so far. And so we did all this work, right? So we've derived this thing. We show that this matrix emits a special factorization. What was this thing called? Rhymes with Molesky. Yes. Cholesky factorization. That's right. This is a symmetric positive definite matrix that could be factorized in a nice way. And life is good, right? So that factorization is a slightly more stable way to compute this thing. But at the end of the day, both of those strategies are using the same basic trick, which is you form this matrix, you factor it, and then you use that to solve the system. Okay? Now, after we did all that stuff, we went back and we solved a slightly different problem, which was like independently of the algorithm we use for solving a linear system of equations, we can look at that linear system of equation and kind of figure out whether or not we expect it to be a stable object to solve, right? And in particular, if we wanted to solve a linear system, maybe we call it, I don't know, Cx equals d, just to disambiguate it from our least squares problem here, right? Then we derived a particular object in the previous couple lectures called the condition number, right? Which at the end of the day is kind of giving us some first order notion of how much x changes in small wiggles in C and D. Remember this story? And in particular, the condition number relative to some norm, which is the norm of C times the norm of C inverse, right? And of course, the condition number is relative to a particular norm. So if we leave the subscripts out, then it's just kind of vague, right? Does our story make sense so far? Now, when we talk about solving linear systems and their conditioning, and then we plug that into the least squares problem, we have to be super careful how we talk about conditioning of this problem. Because in particular, what matrix is relevant here? A transpose A. Do you see that? So when I talk about the condition number of solving this linear system of equation, the relevant thing that I want to compute is a condition number, not of A, even if A is square, but of A transpose A. Now, there's a reasonable question we haven't asked yet, which is like, maybe A is like super well conditioned, maybe it's not. Does that have anything to do with the conditioning of A transpose A? Right? That's the question that we want to answer. Does that make sense? What do you think the just a fun straw vote. Like, do we think that this is going to be a well-conditioned matrix necessarily? Yes? Like super well-conditioned, always, even if the A is ill-conditioned? No? No would be like kind of a weird motivation for this lecture, right? Like, you kind of say like, no, this is fine, and then stop for the day. But no, so this is going to be actually not a particularly well-conditioned matrix. And let's see why. So, in particular, remember that the condition number of a matrix is the norm of the matrix times the norm of its inverse. We'll assume for now that this is invertible. Otherwise, it's very ill-conditioned, right? So in particular, this is like this. Like that. Okay. Yeah, so this is just the definition. And remember that we showed some lemmas that like, when I compute the matrix norm of a product, it's like kind of roughly the product of the matrix norms. It's certainly upper bounded, and in fact, you can show that that bound really isn't that far off. So this thing we can kind of think of, this is a heuristic argument. See the squiggly equal sign here. As the norm of A transpose times the norm of A times the norm of A inverse transpose times the norm of A inverse. Right, if we just expand out all these different products here. Okay? Now, if I take a transpose to a matrix, I think you can convince yourself quite easily that that doesn't really affect the matrix norm, at least for a lot of the definitions we have. Okay, so some of the definitions, by the way, it does, but they're like on the order of the same value. Okay, so what is this thing? Well, we can group together this guy and that guy. We can group together this one and this one. And this entire expression is roughly the condition number of A, if it has such a thing, squared. This is a heuristic argument. Both of these squiggly equal signs are only kind of approximately true, because we're like saying that basically the norm of the product is kind of like the product of the norms. But if you go back to the argument in the previous lecture, you'll see that like this is sort of a Cauchy-Schwarz looking bound. So it's certainly upper bounded by this value. Okay, so let's do a little bit of review. So when a matrix is ill-conditioned, what does that mean about this number? Is it big or is it small? Big. So an ill-conditioned matrix is a big condition number. Okay? What happens if I square a big number? It gets even bigger, right? So in general, this system for solving for x, it works in theory, but it really can mess up the conditioning of the linear system. Right? So for example, let's say that A were a square invertible matrix, right? Then like, certainly I can solve this linear system for x. It's kind of a weird way to do it, but like it's perfectly legitimate. But in doing so, I expect my numerical performance to get worse. And so our goal today is going to be to derive a different factorization which it doesn't suffer from this particular issue because you never actually form A transpose A. You only work with A itself. So in particular, spoiler alert, do I want to spoiler it? Yeah, why not? We're going off book for a second here. We're going to factor A, for now let's say that it's square, as the product Q times R. And for now, let's say A is square and invertible. That's going to actually not be the case what we really care about, but just for now, let's say that it were. Then, and in particular, we're going to have that Q transpose Q is equal to the identity, and R is upper triangular. That's going to be our goal. It looks like LU, except instead of L, we have a thing with orthogonal columns. Okay? We're going to see there are a few different versions of Q. Sometimes it's square and sometimes it's not, but it always has orthogonal columns. So if this expression is true, it may be the fact that Q transpose is not identity. That was the mistake I made in my homework. Many things. Okay. So in this case, how would I get my normal equations? Well, A transpose AX, or A transpose A, well, that's equal to R transpose Q transpose QR, like that, you know? So in fact, this is the identity matrix. So we have R transpose R here, times X, I guess. Oh, no, I didn't write X. Yeah. And similarly, A transpose B. So if we do X, we can stick an X here, here, and here. And A transpose B is going to be equal to R transpose Q transpose B. Right? So if I set these two things equal to each other, then what happens when R is invertible? Well, notice I have R transpose Rx equals R transpose QB. So I can get rid of the R on the left-hand side. And what I'm left with is going to be Q transpose B is equal to Rx, like that. Yes, Axel? A transpose. So if A is QR, then A transpose is R transpose Q transpose.
Okay.
Yeah. And then because there's an R transpose here and one there, when I set these two equal to each other, I just remove the thing on the left. We'll be a little more careful about this and making sure our matrices are the right kind of invertible, but for now, we'll be sloppy. Okay, so at the end of the day, this is going to be the problem that we solve, which is Q transpose B is equal to R transpose X, or Rx, rather. Cool? In doing this process, we never ended up needing to square A, because the way that we construct this QR factorization is going to be directly from A. It's not going to be from A transpose A. Sneaky, huh? And notice, this argument works perfectly well for least squares, right? Because all I did, like this, these two expressions are true. And so long as R is invertible, and we'll argue that it is, then this equality is still true, right? And so this is really a sneaky way to solve even the least squares problem. Isn't this cool? So at the end of the day, to solve least squares, I'm going to do QR factorization followed by an upper triangular solve. Quick review. What's the runtime of that? Well, we don't know the runtime of QR, but after QR, the upper triangular solve is, yeah, quadratic. Yeah. Cool. OK, so that's our story. You can call for a day and get out of here. But that's the high-level perspective. Now, our job today and probably some of the next lecture is going to be fill in the detail. There are a lot of different ways to get to the same factorization. Like for LU, I think everybody agrees that you do Gaussian elimination, you get LU. QR, that's actually not the case. Well, there's like a bunch of different strategies that actually lead to slightly different steps toward the same factorization and have different stability, which is kind of surprising. So we'll cover two in this class, and there's actually two of many. There are quite a few out there. Yeah? That is a good question. I think it's unique up to like a boring, like a permutation or something like that, but I don't quote me on that. Wikipedia is really good at answering that question. The Wikipedia people are really careful about uniqueness. Okay, so in any event, yeah, so this is our basic problem we're going to solve today, and you can see now we have a strategy for bypassing that for the least squares problem. You might ask a reasonable question, which is like, what's the intuition behind this expression? Like, why do these problems get so ill-posed? And actually, this one's pretty concrete. So in particular, let's think about what really is going on here. So let's say that I solve this problem, and then I compute So I solve this optimization problem, and I compute this product, AX. Okay? Let's think about this like kind of geometrically, like how can we interpret this? So in particular, what are we doing? So is it okay if I erase this board? I think this is, it's in the book. It's also a thing you're all very well equipped to do at home. Okay. So now let's think of A as a non-square matrix, okay? So in particular, sadly for us, our board is kind of flat, and like I'm bad at drawing, so the best we're going to be able to do is 3D. Yeah? So let's say that A has 2 columns. Yeah? So then like here's maybe column 1 of A. Here's maybe column 2 of A. So these are just 2 vectors in Rn, or R3. Yeah? So then A times X, what do we know about A times X? Well, it's a linear combination of the columns of A. So in particular, it is in the column space of A, right? It's some combination of the columns of A. Does that make sense? And now I have some other point B. And B might not be in the column space of A. I don't know anything about B. All I know is that it exists. Yeah? And so what is the least squares problem trying to do? It's trying to like kind of weight these 2 vectors so that the point that I get as the linear combination of the weight is as close to B as possible. It minimizes that distance, right? Geometrically, that's what this least squares problem is doing. Does everybody agree with that interpretation? So in particular, like this point here, right? This is, we happen to know it's a right angle. Hopefully you remember that from linear algebra class. That point there is really A times like X star, like the optimal X for the least squares problem, right? Does that picture make sense? So let's think about what's stable and what's not. So in particular, let's think about the angle between these 2 vectors. Right? So let's say that this angle gets really, really small. Right? Now, does the projection change? Actually, not a whole lot. Right? So AX is pretty stable as these 2 vectors get close to each other. I mean, eventually, it's not in the sense that like they coincide and then you have a smaller dimensional space. But like generically speaking, the angle actually doesn't really change this plane. Yeah? But what happens to X? So let me draw a suggestive picture. So I'm going to draw this in the plane. So let's say that here are my 2 vectors, like that. And then B is like some annoying thing like that. Then what's probably the optimal thing to do? Well, it might be to like go really, really far along this guy, and take this vector and go really, really far behind, like to cancel out that little tiny bit, right? So in particular, as this angle shrinks, this becomes a very unstable problem. And that's actually some intuition for why these linear systems for least squares are so unstable, right? That like small perturbations in the columns of A lead to wildly different solutions in this to our least squares problem. Does that make sense? Notice, by the way, that AX is actually pretty stable. It's just X that's unstable. Yeah? Any questions about that like kind of geometric picture so far? So that's sort of our intuition for why least squares can be often lead to ill conditioning for matrices. I guess this picture isn't any better than the one on the board. It's just 2 vectors and a B. But, you know, what you can do. Okay, so now let's go to the opposite extreme. So this is like the really ill-conditioned case, right? And we might say, well, can we kind of judge how far away our problem is from being in this really ill, yucky condition case? And in particular, we might ask, like, well, when is my system really well-conditioned? Yeah? Now, you know, there are lots of matrices out there in the universe. What's probably the easiest one to invert? Identity. Yeah, I think we can all agree on that. Identity is pretty easy to invert. Constants times the identity also are not so bad. But, you know, identity is good enough. Okay? So, in particular, let's say, so wait, and by the way, with respect to the 2 norm at least, the condition number of identity matrix is equal to 1. In fact, I think with respect to almost any reasonable norm, that's probably true. Okay, so in that case, like what do we kind of wish happens in life? Is somehow that like, it would be really great if like A transpose A is like roughly like the identity matrix, right? Because if that's the case, then we're really good at least squares. Now, does this condition, is this equivalent to A equaling the identity even if A is square? No, right? Obviously that is sufficient, but it's not necessary, right? This is not the same thing as A being identity, but rather this is a different condition called orthogonality, right? Okay, so let's interpret orthogonality a little bit. We're going to move slowly for now, and then I'm going to hit you over the head with a really ugly matrix factorization. That's my plan. So sneak up by surprise, like lull you into a false sense of comfort with like undergrad linear algebra here. Okay, so In particular, let's say that I have a matrix that satisfies this. Incidentally, it is often, what's the word I'm looking for? Convention, that when a matrix satisfies this condition, we use the letter Q, hence QR factorization. So let's say that Q transpose times Q is equal to identity, and we want to kind of like dig in and interpret a little bit, like what does that condition mean? So remember, so here's my little schematic. So let's say that Q has columns Q1 through Qn, like I've shown you on the board here. And now, what am I going to do? If I take Q transpose, I take all those columns and I just flip them on their sides. Right? So that's this first line here. So if I do my matrix vector product, I could do it on the board, but I feel like you guys actually at this point are probably okay with the screen math just for this little bit. Then Q transpose Q, what are the elements of this matrix by this interpretation? Well, it's the dot product pairwise between every pair of columns of Q. Okay? So in particular, if this thing equals the identity, then we have the following property, that Qi dot product with Qj is equal to 1 when I is equal to j, and 0 otherwise. Yeah? Okay, so this property has a name, right? This is, and this is all linear algebra review. So like this means that your set of matrices is orthonormal, right? Meaning that they're all length 1 and they're all perpendicular to each other. Right? That's what this condition means. Any questions so far? Cool. All right. So incidentally, of course, geometrically, we can sort of ask what does orthonormality mean. So for instance, let's say that I have a matrix with orthonormal columns, Q. And now I take a vector and I multiply that vector by Q, and I compute its norm. Then what do I get? Well, and in fact, let's just do the second one, because obviously if I take x equal to y, that's a special case, right? So Qx dot product with Qy. Remember, our dot product thing says this is the same as x transpose Q transpose Qy, right? And this thing we've decided just by fiat is the identity. So what we're left with is that this is equal to x dot y. So in fact, Q is a matrix that preserves dot products. Remember that dot products are like lengths and angles, right? So Q is basically a rotation or a reflection, but it's not a stretch or a shear. Okay, so that's geometrically how to think about it. In fact, here's a picture of a rotation, in case you forgot. Okay, so I think this is probably a good linear algebra review. Nothing too exciting so far. I'll pause here. On your homework, there's a problem that says the following. It says, suppose I have a function which preserves distances on Euclidean space. So I have two, if I take 2 points and I put them through my function, and the distance between their images is the same as the distance between their inputs, that property is called isometry. It's distance preserving. Then the homework asks you to prove that that thing can be written as an orthogonal matrix plus a shift. I would suggest you start that problem earlier than you think you should, because it's actually one of these facts that I think we all think is intuitive and true, but actually proving it was something I had a little bit of trouble with. It took me a bit. And then Chris told me it was unreasonable to put on your homework, so I left it there. Okay, so anyway, it's a good little math challenge. Obviously, by the way, it's a thing you can Google, but don't, think about it first. Yeah. Okay. So, right, so to summarize our picture so far, least squares is somehow easy when our columns are orthonormal, and it's somehow hard when our columns are like very close to parallel, right? That's our story so far. Okay. So here's the thing. Somehow it would be really nice to expose that least squares structure in our matrix, right? Like in particular, let's say that all I cared about was exactly this, that I solve our favorite problem, min x a x minus b. And now I compute, right, that gives me x. But really I wanted the projection, I wanted ax. This is a very common situation. Like maybe A contains like ingredients I have in my kitchen. I have some recipe that I can't actually make. I find the closest projection, and now I actually just want to do the recipe, right? Then let's say the object I really care about is just ax. This is slightly different than computing x. I don't care about the weights. I just care about the a. Yeah? So in that case, what am I really doing? I'm computing the following. I'm computing the projection. There's an r there in case you're wondering. The projection onto the column space of A of B, right? That's really the calculation. That's the composition of these 3 steps. Does that make sense? I'm sorry, there was a lot of bad handwriting that just went into this. I could fix it, but I'm choosing not to. Okay. Here's the thing. Does the column space, do I need A explicitly to project on the column space? In particular, like, notice that I can do whatever I want to the columns of A as long as they stay in that linear subspace and the column space doesn't change. Right? In particular, like, remember our picture, so we have these like two extremely long vectors. But these are really two vectors in the plane, right? If I somehow manage to map these guys to like this guy and then another one, which is just 90 degrees to it, so long as these two vectors are in the same plane as what I started with, then this guy will remain unchanged. Does that make sense? Like, pause to think geometrically for a second. You guys look suspicious, but I don't see people raising their hands. Yes?
Is it basically scaling?
Yeah, scaling, or I could like take a multiple of the first guy and add it to the second, for example, and that's perfectly fine, right? Because all that I care about is the column space. I don't care about the weights x. I just care about the column space. Okay? And so what we're going to try and do is essentially to expose that structure. And in particular, there's an algorithm you probably learned in linear algebra class which does exactly that, right? Which says, I have a collection of vectors, for example, the columns of A, and instead of working with that collection of vectors, I want to map it to an orthonormal collection of vectors that spans the same space, right? This is like a thing that you've probably encountered in linear algebra class. Remember what it's called? This is Gram-Schmidt, right? This Gram-Schmidt algorithm. You have a collection of vectors, and like you don't care about the directions of the vectors, you just care about the space that they span, right? And so you're going to orthogonalize them. So remember how like LU factorization, we got there by doing what we were already doing in college calculus class, like Gaussian elimination, and then we just kind of codified it. We got a matrix factorization. Now we're going to do exactly the same thing, but with this Gram-Schmidt technique, and we're going to get QR. I'm sorry, I gave it away. You could, that's that. Okay, but first we got to prove a few lemmas to make sure that like what we're doing is like kosher. So let's double check that. So in particular, what we're going to prove is this kind of intuitive fact that if I take a matrix that may not be square, so that's A, and I post multiply it by a matrix B that's invertible, so that one is square, that the column space of A equals the column space of AB. So to like go back to Paul's comment earlier, he was saying like, for example, like this is scaling, right? So scaling clearly, notice that it's post multiplying because I'm acting on the columns of A. So I would like post multiply by a diagonal matrix to scale the columns. So that would be an example where like if I scale a column, I haven't affected the column space. Or similarly, if I added one column to another, that's kind of like substitution matrix, right? That's going to be okay. Cool? Okay, so let's prove this fact real quick. Ugh. So for proving these boring facts from linear algebra, I think it's important to not think, right? You just follow your notes. It's the toucan-Sam approach here again. So in particular, we're going to take an element of the column space of A and show that it's also in the column space of AB. Then we're going to take an element of the column space of AB and show this in the column space of A. Yeah? So, which one do we want to do first? A. Okay, so. Fine. Okay, so take. No, now I'm committed. It's fine. So, right. So let's say that I have a vector B in the column space of A. Then, in particular, there exists an X such that AX equals B. This is actually the definition of column space, right? There's some way to reweight the columns of A to get B. Okay? All right. So what am I trying to show? I'm trying to show that there's something where ABX equals B. Yeah? Well, notice that AB times B inverse X is equal to B. I haven't done anything, right? But we know B is invertible, so that's okay, right? Because this product is just the identity. I just stuck the identity in there. Well, so what does that show? That shows that AB times this thing equals B. So in particular, B is in column space of AB. You see that? Because I found a vector where if I multiply it by AB, I get B. So by definition, it's in column space. Okay, check. So now take, I'm going to try and use my C in column space AB. Implies that there exists some y such that A, B, y equals C, like that. But notice that just by factoring it this way, A times by is equal to C. So in particular, C is also in column space of A. C is in column space of A, which is what we want. Okay? Any questions about that? So like, it's important when you see lemmas like this to think intuitively, like, what is this really saying? So this is saying that like, if I take a bunch of vectors, which are the columns of A, and I do boring operations to them, like I combine them and mix them up in different fashion, then like the vectors themselves might change, but their span remains the same. Right? That's all. I can't like introduce some new direction in the span. Okay. But that also gives us a clue as to how we're going to get to QR, right? We're going to start with a matrix. And remember, like, what does Gram-Schmidt do? It starts with a set of vectors, and it starts doing stuff at them until they're orthonormal. Now we're going to take a matrix and kind of post-multiply it by invertible stuff until I get orthonormal columns, right? That's going to be our strategy. Okay. Right, so yeah, so in particular, invertible column operations don't affect column space. Notice this is where QR and LU start to diverge, right? Because when we were doing Gaussian elimination, we were doing row operations, right? We were multiplying on the left. Now we're going to do column operations, we're multiplying on the right. Okay, so this is our strategy. We take A, and we start multiplying it by stuff, right? So like we're going to take A, and we're going to keep multiplying it by different upper triangular matrices that are invertible. Maybe, yeah, well, whatever. And then we're going to get orthogonal matrix Q, and then we're going to say, well, we invert all this stuff, put it on the right-hand side, and that's going to give us our QR. Right? This is a very similar argument to how we got LU. Cool? Cool. This is fun. I like this stuff. Okay. Okay. So, and that's going to give us this thing. And like we already showed, essentially, if we want to solve our normal equations, it's very easy to do that. And because our procedure never formed A transpose A, the stability issues that we're worried about are a little bit less problematic than before. Okay. All right. So in order to do that, we're going to start by remembering that Gram-Schmidt algorithm. Yeah.
Sorry, just maybe big picture.
Mm-hmm.
Is QR therefore going to always be more stable, or is it just that it's sometimes for certain A's it's going to be more stable?
I think that's a good question. Like, is that an always kind of thing?
Yeah.
I think the short answer is we haven't shown that.
Okay.
But I think certainly the mythology is that this is the preferred choice. It's a good question, yeah. I wonder if there's like some weird matrix out there for which, for whatever reason, that feels doubtful to me, but I don't have a smart argument. Yeah. I can't speak to it. Okay. So our plan of attack is going to be, we're going to remember the Gram-Schmidt algorithm, and then we're going to recast it in terms of elimination matrices, and then we're going to get QR. Then we're going to realize that that's a terrible algorithm, and then do the one that people actually do. So our first job is to convince ourselves such a matrix factorization kind of should exist, and then we're going to go back and do the like totally non-obvious technique that gets it in a more stable fashion. Okay. Right. So in order to do QR factorization, we're going to essentially remember how this technique works. So we start with a collection of vectors. We don't know anything about them, and then we're going to kind of progressively add one vector to the set, while maintaining orthonormality. By the way, I'm saying all these words. Have we encountered Gram-Schmidt algorithm before? We're just like orthogonalizing a set of vectors. So yes, except for the people that refuse to raise their hand. Yeah. If you haven't, it's okay. Just speak up. No. Okay. I'm taking your word for it. I'm a nice guy. I'm not scary. Even though I got an email from the math department saying they're intimidated. All right, so we'll come back to that later. Right, so what we're going to do is we're going to think about projection first, and then we're going to use that to orthonormalize stuff, because essentially our procedure for orthonormalization is going to go as follows. So I have a collection of vectors. I'm going to take them one at a time, and I'm going to normalize them, so I might change their length. So maybe this is vector 1. Now I've scaled it, so it has length 1. So I just divide it by its norm. Now with vector 2, I'm going to subtract off its projection onto the first guy, and then what I'm left with is an orthogonal one. And then for the third guy, I'm going to subtract off its projection onto the last two, and so on. Right? This is the Gram-Schmidt algorithm. So the first thing we have to do is remember the projection formula. Yeah? So let's do that. So this is the world's most boring least squares problem, which is what multiple of a vector is closest to another vector. So in particular here, our variable is going to be c, which is just the multiple. So in particular, ca minus b squared. Well, we kind of only know how to do one thing in this class, which is to take things that are squared and expand them. Right, so let's do that. So we get c squared mod a squared minus 2 ca dot b plus mod b squared, like that. Yeah. This is a quadratic, so if I want to minimize it, I take the derivative and set it equal to 0. Or you just remember that little formula for the vertex of a parabola. Let's pretend like I remembered that because it's in my notes. And in particular, the minimum of this is going to be a dot b over mod a squared, like that. Right, so this is just take derivative with respect to c and set it equal to 0. Cool? Okay, so in particular, this means that the projection onto A of B, right, which is what we're kind of doing here, well, that's equal to C times A, which is equal to A dot B over mod A squared times A. Okay, that's supposed to mean A, by the way. Notice, by the way, if I took this A squared and I kind of distribute it, like there's an A here and an A there, right, then what is this kind of doing? It's like normalizing A and then taking the dot product. There's a lot of different ways to interpret this expression. And moreover, so I keep drawing this picture, right, that I like have, you know, two vectors, I project like that, right? So this is the projection. And then I keep saying that this is actually orthonormal, so we should probably double check that, right? So in particular, let's say that I subtract, so I have A dot product, the difference, so B minus the projection of A onto B. Right, so what is this vector? That's this guy here, right? Because this is B, this is projection A of B, yeah? Okay, so what is this thing? Well, if we distribute this product here, this is A dot B minus, and then we have this thing here. So it's going to be A dot this guy, so it'll be A dot B over mod A squared times A dot A. Like that, right? And of course, these two are the same. And then we have A dot B minus A dot B, so that's 0. Okay, so our picture holds true. The universe hasn't collapsed yet. Okay, fantastic. So now we can take projectors and project them on, vectors and project them onto each other. Essentially, we've kind of derived this nice little set of geometric relationships, right? The projection is obviously parallel to A, kind of a definition. And moreover, the difference is orthogonal. Okay. So let's say that we have now a bunch of orthonormal vectors, because that's what we're building up one at a time in Gram-Schmidt. And I want to project B onto the span of all the AIs. Right, that's really our goal here. Then, of course, now we know that the projection on any one AI is going to be this formula here. Right? Because remember that because they're orthonormal, the length is equal to 1. So this A squared goes away. Does that make sense? Okay, so in particular, one thing that we can double check, so let's say I want to project B onto the span of all the A's under the assumption that they're orthonormal. That's what the hat means, right? If I expand this square, what's going to happen? Well, all the cross terms are going to go away, right? Because now every time I have like A1 dot A7, we know that's 0 by definition. So if you think about it, what I'm left with is the sum here. Does everybody agree with this? I can write it out on the board, but I think this is mostly review. Okay, and notice that this is exactly the same as the problem we had on the board here. Yes, excellent. No such thing. Oh yeah, exactly. So for now, k is just a number. So I have a collection of orthonormal vectors a1 to ak. I have another vector which is maybe not in that span, and I want the projection. Right, so this is the least squares problem I want to solve for the C's. Okay, I take this least squares expression on the left-hand side, I just expand the square, so I get a bunch of dot products between all the different pairs of terms. But remember that ai dot aj is equal to 0 if I is not equal to j. Okay, so in essence, I can remove almost all the cross terms from this thing, and what I'm left with is the right-hand side. Okay, So when I solve for C, I basically get a formula that I think you guys already knew, which is just that like if I want to project B onto the span of the AIs and they're orthonormal, then the coefficient in front of each AI is just the dot product. That's all. Okay? So to codify that, we get this expression down here. This only works for orthonormal vectors. Everybody with me so far? I'm rushing only because I think this probably is review. Okay, so this leads us to our favorite algorithm here, which I'm realizing I have typeset incorrectly on the slides. That's such a slide. Okay, which is the following. So our input is some collection of vectors v that I can't say anything about, right? So here's what I'm going to do. I'm going to start with v1. I'm going to divide it by its length. That's rescaling. Now what do I know? I know v1 has unit length. Now I'm going to take v2. I'm going to subtract off its projection onto v1 because I kind of don't need that piece. I get a vector r and normalize it, and that'll be our second guy. Does that make sense? And if I repeat this procedure over and over again, so now if I have v3, I subtract off its projection onto the span of v1 and v2, and then normalize, and so on. That is our Gram-Schmidt technique. Does that make sense? Okay, so let's write some pseudocode. If I have a set of vectors v, then essentially here's our little for loop. Then I go from 2 to k, and each time I compute its projection, I subtract the projection, and I normalize. And then here's a claim that I think we're not going to bother proving it because at this point it's a little pedantic on the board. But like essentially, the span of the a hats and the spans of the v's is the same. Okay. Where can this algorithm fail? Yeah. So in particular, I mean, if you just look at the operations in this technique, there's one of them is a little fishy. Right? We can also always, like, multiplication is always fine, but division can lead to a problem because infinity is a hard number to think about. Actually, I have a bumper sticker on my car that says that. And in particular, step 2.2 here is going to fail when v minus p is equal to 0. In other words, like when the projection is just equal to v. So like my set of vectors is redundant. Okay. And moreover, by the way, this algorithm can be very unstable when I'm close to that space, right? So like if I have two vectors, like this picture over here, that are nearly parallel, then notice that this little residual term, r, is going to be really tiny, right? So I'm dividing by a small number, and that's an unstable operation. That's essentially why this Gram-Schmidt algorithm can be kind of problematic. Does that make sense? Okay. So here's a fact I don't think we need to actually derive a. So essentially, think about the steps of the algorithm that we just derived, right? So let's say I start with a matrix A, and now I'm gonna just use A as my data structure for storing all my vectors. I'm gonna apply Gram-Schmidt to it, right? Then as I do that, what's gonna happen? Well, I can take A, and maybe I rescale a column because I divide it by its length. If you think about it, that's the same as taking my matrix and post-multiplying it by a matrix that's has the form like 1, 1, 1, 1 over the norm of vi, 1, where this is in the ith slot, right? That's how I rescale stuff. Okay, and similarly, like what else do I have to do? Well, I have to compute the projection and then subtract it. What is that matrix going to look like? Well, I'm going to start with v. I've got the identity matrix kind of built in there because I'm subtracting off p. That's okay. And then I'm also I'm subtracting off multiples of previous stuff. So what kind of matrix is that? Well, if you think about it, it's actually upper triangular, right? So I've got a matrix with like identity down the diagonal. That's the part that's kind of leaving v alone. I need to subtract off the pi's, but those are all contained in this part of our thing here, right? And so that's our basic trick in LU, or in QR factorization. Okay, that's going to be our trick here is to get our factorization. In fact, actually, it's a little bit annoying to see the projection formula from this way. There's a different way to carry out Gram-Schmidt, which is actually identical to the Gram-Schmidt formula, where what I'm going to do is start with my vectors, and rather than looking backward and projecting everything out, I'm going to take a vector I and project it out of all the remaining ones. Right? And from that, it's, I think, more obvious that R should be upper triangular. Yeah. Okay. Right, so the bad case for Gram-Schmidt is illustrated here, right? So like I have two vectors, I have V2 and A1, I project it, and now there's this tiny little residual that I'm dividing, and that's where things get unstable, okay? But at least we've convinced ourselves that like in math theory land, like a QR thing should exist, so long as the columns of my matrix are linearly independent, right? If they're dependent, I get a 0 and something goes wrong. Cool? Okay. This is what I clarified in the textbook chapter, by the way, that if you do this one, this only works for things with linearly independent columns. Okay, so now, and so that was our first strategy, is to kind of post-multiply by upper triangular matrices until I obtain Q, and then I have my factorization, right? So in other words, I'm taking a matrix and I'm kind of editing it to be closer to orthogonal. What do you think is going to be my other strategy? Well, now I'm going to pre-multiply by orthogonal stuff until it looks upper triangular, right? So if I take A and I pre-multiply it by a bunch of orthogonal matrices until I get an upper triangular thing, then what I'm going to be left with is QR factorization from kind of an opposite perspective. Does that make sense? So I think if you look at the history of QR, this is really what happened. Like Gram-Schmidt has been around forever. Gram and Schmidt are old. And then somebody noticed that that implies this matrix factorization. And then you kind of look back and you say, well, wait a second. We did LU by doing row operations, not column operations, right? But now our row operations aren't triangular matrices anymore. They're orthogonal, right? So we have to do something a little different. Does that make sense? That's the only difference. And the strategy that we're going to introduce here is one of many, by the way. Like, this is not a standard. There are lots of different ways to do this. But it is one of the very first ones that was proposed, and I think actually is the very common standard in numerical linear algebra code. Okay? And that is a strategy that uses something called householder reflections. Fun fact, householder is somebody's name. It's not like a homeowner. Okay, so the basic point here, like if you remember back to how we did LU, we like worked with a very specific kind of formed matrix, right? This upper triangular elimination matrix. And we showed that we could just keep pre-multiplying by these things, and eventually we end up with an upper triangular thing by pre-multiplying by lower triangular elimination stuff. So now we'd like to do something similar, but instead of doing elimination, they need to be orthogonal, right? Like elimination matrices are lower triangular, but they're not orthogonal. And so we need some class of interesting orthogonal matrices that can kind of help us do something very similar to Gaussian elimination. Do you see that? That's like sort of our job here. Any suggestions? Is householder in the room? No? Yeah, no behind you. Yeah, so it's like not entirely unobvious how to do this kind of thing. And so I think what happened, if you look at the early inspiration for these algorithms, is people just thought of like, what are things I can do to vectors that preserve their lengths and angles? And then try to kind of translate those into matrices, and then see if you could build an algorithm out of them, right? Really. And so like in particular, there are going to be two obvious things you can do, which is reflect and rotate. Right? Rotation preserves lengths and angles, and reflection over a plane preserves lengths and angles. Yeah? And so basically the two dominant algorithms for QR factorization that operate on the left-hand side, one of them is by reflection and one of them is by rotation. Yeah? So we're going to work out the reflection version. The rotation one is left as an exercise in the textbook. I added it to your homework, then I removed it because I hate it. Okay, so let's do that real quick. So let's talk about reflection. We can reflect upon. Never mind. Okay. Okay. And I think now we're going to be firmly outside of the territory you're likely to have seen if you've taken undergrad linear algebra, but not numerical methods specifically, because this is a little specific. Okay. So let's say that I have two vectors. We're going to give them a name, which I'm thinking of right now. Which is the following. So we're going to have a vector, I'm going to draw it really long, v. So I'm trying to like facilitate math drawing diagrams before having actually written the symbols there, which is always annoying to do. Okay, and in particular, I have a vector b. There we go. Here's going to be my goal. So v and b, there's two of them, so they form a plane. Fun fact. And I'm going to compute the reflection of b over v while remaining in this plane. Does that make sense? So how do I do that? Well, I can do it in two steps. Well, I can compute this vector, which is going to be the projection of b onto v, like that, right? And now I can take this displacement here. So what is this? This is projection onto v of b minus b, right? That's the difference. And notice I've drawn the head of the arrow this way. And now I can take this vector and I can just copy it down here, like that. And I can draw another vector downstairs. And this guy is going to be a reflection. So here I've got another projection onto v of b minus b. And the question is, what is this thing, right? So it's b plus 2 times this vector, right? So this guy is equal to b plus 2 times the projection onto v of b, like that. Does that make sense, how I got this picture here? Incidentally, it's also on the screen. Ta-da! Like that. And so let's actually work out the formula for this thing. So, did I do this right? Oh, I didn't. But you guys are so agreeable. You didn't even catch, right? Because this is 2 times this minus b, right? So it's really like that. Yeah. Now, do you agree, or we're just like totally comatose today? We're not gonna. Okay, cool. So in particular, we've got a b and a minus 2b. So this is really e equal to 2 times the projection of v b minus b, like that, right? Okay. And conveniently for us, we have a formula for that, right? So this is 2 times v dot b divided by v dot v times v. Now I'm actually going to write v on the left-hand side for a second. Okay? Minus b, like that. Right? Remember, this is our projection formula? Okay. And now notice that there's like a b here, and there's another b there. Yeah? So in particular, if I kind of group the v's like that, I can write a different expression for my matrix, which is as follows. This is equal to 2 times v transpose over v transpose v minus the identity all times b. Cool? Does everybody agree with me? So notice that this is kind of neat. Do you see what I did? Like, what is this matrix? This thing takes a vector, whatever it is, and then flips it over v. So I've kind of factored the reflection away from the particular vector that it's acting on. Yeah? Okay. So now we're going to do something that I find very irritating from the mathematical literature, because it's like begging for a sign mistake. But by convention, and I'm going to do it because it's householder's fault and we should have textbooks that agree, we're going to call this minus HV. Okay? So when people talk about the householder matrix, it's actually you reflect and then you flip the sign. Yes? Oh, H sub V. Yeah, good question. Because remember that H is a matrix constructed from V. Yeah. Any other questions? That's a good one. So by the way, if you want to know why householder did this, I think the other algorithm for QR is something called Gibbons rotation, which is going to have like cosines and sines, like it's like rotating stuff. And that one is orientation preserving. Notice that like this operation flips the whole universe. So like the determinant flips every time you apply it. So I think like why the minus is here is just to kind of cancel that out. But that's my best guess. I don't know the history here. Okay. So anyway, I see that. But just to summarize, like HV is a matrix construction from V of this form. Notice that like this makes sense as a matrix because I have V transpose. And it takes a vector B, it reflects it over V, and then it flips it with a minus. Yes, Paul.
When you say reflection, you mean on which plane are we talking about here?
So this is in the VB plane, right? This whole picture is on the blackboard here, right? It's a good question. So the components that are orthogonal to this plane just get left alone. Yeah. Yes?
And rotations usually have just a determinant of 1.
Yeah.
A negative determinant rotation is just because it's the flip of the
I would argue that there's no such thing as a negative determinant rotation, right? So there's a difference between like ON and SON. But yeah. That's a terminology, right? I think usually when we think of rotating, we think of literally rotating, like not the universe flipping inside out. Yeah. Okay. Cool. So this is the householder matrix. And here's going to be our basic algorithm. We're going to construct a sequence of V's that kind of simulates Gaussian elimination. right? So I'm going to like start with my matrix, and I'm going to pre-multiply it by these HVs until I end up with one that's upper triangular. And notice that this guy is an orthogonal matrix, right? This clearly preserves length. It's just reflection. Yeah? So that's our trick. Any questions so far? That's actually like really the intuition. We have to do a lot of calculations to get there, but like that from a high level, like I think this strategy is like completely reasonable. Okay. Cool. By the way, here's a cleaner version of the same formula. Yes, Asa. Why are we reflecting stuff? It's a good question. Because Householder decided that was a good idea. No, I think the higher level point here. Remember our goal. So eventually we want to have A equals QR, right? So in Graham-Schmidt, we started with A, and then we started post-multiplying by R's, like upper triangular stuff, until we got to a Q. Now we're going to do the opposite. We're going to start with A. We're going to pre-multiply by like QI this way until I get to an R, right? So we need a class of QIs, right? I need some set of Qs to work with. So just the way that like we had elimination matrices for Gaussian elimination, here's the hypothesis, which we have not actually verified. That's our next step, is that we could come up with operations only involving these guys that kind of simulate Gaussian elimination. We haven't done it yet, but this is our hypothesis. So far all we know is that this is some reasonable class of orthogonal matrices. Yeah. Yeah, it's just like, essentially, I think that like literally Householder's idea was just like, I need a class of things that are orthogonal and can be written in closed form. And this is one. And the other one is rotation. Yeah, both of them work. Okay. So in particular, let's see if we can carry that intuition out. Okay. So what does Gaussian elimination do? I take a matrix. Remember our favorite like little playbook here? We like take a matrix A. So like this, so maybe I have A is equal to, and then I just have a bunch of X's. I don't know anything about it. And let's say I want to do one step of my QR algorithm, and I want to do it in kind of an analogy to like how I did LU. Then I want to take A and pre-multiply it by something, Q, or namely HV, for some carefully chosen V, that has the following property, that puts some element, maybe C for now, like because it's so like rescaling is easy enough, right? We're gonna have C times a bunch of zeros, and then nothing else, right? Because this looks the same as Gaussian elimination algorithm, right? Like so, in the first step of forward substitution, I pre-multiply by a sequence of matrices that puts a 1 up here and then zeros underneath the diagonal. Right? So our algorithm is going to do the same thing, but rather than doing forward substitution, it's going to apply a weird matrix HV. And then our next step is going to be one that takes this guy, puts a new constant, and then the zeros down the diagonal, and so on. That makes sense? That's our strategy. And again, notice we're like totally reverse engineering an algorithm, right? We're saying like, well, it'd be really nice if HV existed so that we could do that. But we don't actually know that it does. Yeah? And that's literally, if you look at how people do exposition of this technique, that tends to be how they do it. Okay? Everybody with like the high level strategy here? So at the end of the day, if we isolate the first column, okay? So let's give this thing a name. Let's call it A. It's really A1, but we're just gonna work with the first column for now, so I'm gonna call it A, okay? Then what would I like? I'd like that HV times A is equal to some constant times, times, so I want C and then a bunch of zeros, so in particular I want C times E1. I'm sorry, it took me a minute to get that sentence out in one piece. Does everybody agree with me, this expression, that if I could find such a V, then I've done the first step of Gaussian elimination? Right, because notice that now when I multiply by A, I can't say anything about the remainder of this matrix, but I at least know that the first column looks like this. Yeah, I saw a hand and then it went back down. No? Okay. All right. So what we're going to do is just take this expression. We have an expression for HV. We're going to plug it in, and we're going to see what it implies, and then notice that our math kind of goes backward, like it's an if and only if. Okay? So, in particular, Yeah, so what is HV times A? Well, this is really equal to identity minus 2VV transpose over V transpose V, all that times A, right? I just plugged in the definition of HV. Notice the sign flipped because of this stupid minus. Okay. What is this thing equal to? Well, if I expand it out, this is equal to identity times A, so this is just A, minus, and then we have 2V, V transpose A, so that's the dot product between V and A times 2V. Yep. So in particular, we have 2V times V transpose A over V transpose V. In essence, we're kind of like undoing the derivation of H that we did before. Okay? Okay. So we have C eq1 is equal to this expression here. Right? Remember, our goal is to kind of solve for V. Yeah? Okay. So it would be really nice to isolate V. And conveniently for us, we can kind of do that. Notice that there's a V here and kind of nowhere else, almost. Except that it's like kind of in this ratio, but like we're going to ignore that for now. So in particular, if we are able to find such a thing, then what does that imply? That implies that we must have the following form for V, that V is equal to A minus CE1, right? So here I've just moved the CE1 to the other side, right? All of that scaled by V transpose V over 2 V transpose A. Do you guys see what I did here? I said that I have this equality, and then I just solved for V by multiplying by the inverse of this fraction here. Any questions so far? And again, this is a really weird type of hypothetical math we're doing. We're saying, like, if such a V exists, then it certainly satisfies this expression, right? And the reason that we're doing that is we're trying to get a feel for, like, what is V going to be at the end of the day? Yeah? Uh-huh. Not quite. You have to be a little careful. If you think about it, so A is whatever it is. Yeah, so in this case, A would be, yeah, you're right, B in this picture. The bottom line would be C times E1. So what it's trying to do is to find the vector over which you would flip to get E1. Mm-hmm. Yeah. You have to be a little careful here. Is that right in general? I want to say no, but you're right that I'm struggling to think of it at the moment. You're saying the average is good enough? I'm going to think about that. Yeah, no, you're right. Oh, you know what? Because of the minus, it's not quite right, but that shouldn't make it much more complicated. I'll come back to your question. We'll check it when we're done with the calculation. Good critical thinking here. And actually, a clue which supports your thesis is notice that one thing that we can say for sure is that V is equal to this vector scaled by some constant. So in particular, we know that V is parallel to A minus C times E1. So it's like somehow in the span of these two guys. Yeah? Okay. So that much is true. I'll have to think about your question to see. We'll see when we get to the end of this whether it's right. Maybe we're doing a really complicated calculation that we could have done more easily. Wouldn't be the first time in my life. Okay. So one thing that's absolutely true is if I take V and I scale it up and down, it has no effect on HV, right? Because like we normalize V when we do that projection. So in particular, since we can scale V any way that we want, we're going to just choose V to equal this expression. Okay? So you're going to choose V to equal A minus CE1. And now our question is, what is C in this case, right? Remember, this is all this kind of weird thing that's saying, suppose V exists, then we must be able to write it in this form, right? And so we're kind of working in the wrong direction in a sense, but then we're just going to read all of our equalities backward and show that it's okay. Okay? So Right, so in that case, right, what do we know? We know that V is equal to, like we have this expression here, right? So in particular, we have that V is equal to V times V dot V over 2V dot A, like that, yeah? Why is that? Oh, yeah, so this is right. So we just chose this thing as equal to V. So then like by this equality up here, this is just a weird way to write it, yeah? So in particular, that means that this ratio is equal to 1, yeah? Okay, so we have that 1 is equal to V dot V over 2V dot A. And if we expand out our formula for V here, we get that this is the norm of A squared minus 2C E1 dot A plus C squared. Divided by 2 times the norm of A squared minus CE1 dot A. Okay, so all I did was just plug in this expression and calculate these dot products. Whew. Okay, this thing's equal to 1. So then if I multiply both sides by the denominator, notice that a convenient thing happens. We have a lot of terms in common. Yeah. So in particular, when the smoke clears, notice that like we've got a 2CE1.A. We have a 2CE1.A in the numerator. Yeah. We have 2 norm A squared here and then A squared there. We've got a C squared here and no C squared there. So when we simplify this thing, we're just going to get C squared is equal to mod A squared, like that. So in particular, C is equal to plus or minus A squared, like that. Oh, not squared, sorry. Okay. Notice that, by the way, once again, the sign of V doesn't really matter. Like there's a lot of choices that we could make because if we like flip the vector along with we're projecting, like nothing really changed. Okay. So all these steps are actually reversible. I can just read my entire proof backward, and you'll see that everything is perfectly fine. And so secretly, what we've shown is if we take this choice of C, and we read it all the way back around, and we read this whole argument backward, what we're going to show is that if we take V equal to A minus CE1, then this product puts a C up here and zeros down the rest. Sneaky, huh? So what did we just derive? We derived, and HV, by the way, satisfies the property that HV transpose times HV is equal to identity. We didn't actually check that, but you can. It's just algebra. Okay? So what did we do? We started, I think it's really easy to lose the forest through the trees in this argument. So we started with a generic matrix A, and we showed that for a very carefully designed HV, when we multiply it by A, we get that the first column is some matrix times E1. Some constant times E1. Cool? By the way, the constant could be 0. That's actually fine. So that's where this algorithm is actually a little better behaved than like some other strategies for QR. Do you see that? Because like here I can, if these columns end up being linearly dependent, then I'll just get a 0 in that slot. But that's actually fine. Yeah. Okay. So that's our analogy to forest substitution. We do all this math. I'm going to have to come back to your question whether it's the average or not. Looking at it, it's not obvious to me, but we'll have to think it. Yeah. Yeah. Oh, you're right. Yeah. So I guess it is the weighted average. Yeah, you're absolutely right. So this thing, unsurprisingly, our colleague is absolutely right. We're playing this funny reflection game where like we've got some generic vector A. We want some multiple C E1. And so essentially, it's the midpoint that goes through them. That's the thing we're going to reflect over. Yeah? And so we just kind of worked through the algebra and showed that this picture is actually the case. Yeah, good point. Fantastic. I should throw this in the textbook. Yeah, never really thought about it. It's just dumb because it's the obvious question to ask. But thank you. Okay, so now, so far, we have this. So now what are we going to do? Well, it's just exactly the same thing, but with this lower n minus 1 by n minus 1 submatrix, right? And in fact, one thing we can choose is that one thing you can argue is if you can basically go through the same argument we had before, but now we want if we take A and kind of split it into two pieces, one of which is just going to be what it was before, and then the other half is a 0, right? Then you can work out exactly the choice of V, and you'll get something very, very similar. Yeah. Actually, there's two different ways to do that. That's one. Another is to do the 1 unit smaller householder matrix and then put an identity in the upper left. Either one will turn out to be equivalent. Yeah. OK. So when the smoke clears, here's what we've essentially done. We've chosen a sequence of V's. Notice that there's 1 per column of my matrix. Right? So there's V1 through Vn here that I pre-multiply by A to get an upper triangular R. And this algorithm, by the way, unlike our algorithms for LU and even for Gram-Schmidt, will succeed when A is singular. That's actually OK here. You'll just end up with a 0 in a column because we didn't actually specify that this C constant has to be non-zero. Yeah? There's one little border you have to worry about, which is if V is 0, then just by convention we call HV the identity, and then you can convince yourself that works. Right, so the good news is that the inverse of the H's, because they're orthogonal, it's just their transpose. Right, so it's very easy to get Q. And then once you have Q, there are a lot of different ways to get R. One of them is to just do this calculation. Another one is to like maybe solve the linear system for R. Either way. Right, so in particular, notice A is equal to QR, right? So if I know Q, then I can get R as just R is equal to Q transpose A, right? So even if I forgot R, that's actually OK here. Or vice versa, right? If I only remembered R, I can get Q by upper triangular solve. OK. Right, so that's our basic algorithm here. One note, sometimes, so notice that Q here is a square matrix, right? So let's say that A is M by N. Then how big is Q? M by M, right? So remember the least squares problem tends to involve very tall matrices, right? So it could be like 1 billion by 2 would be a very big data set of 2-dimensional points, right? So in that case, all of the H's here are going to be 1 billion by 1 billion, right? Maybe I don't want to store that matrix. But the good news is that I can reconstruct Q by just storing the sequence of V's that it took me to get to Q, right? And there's only 2 of them. So that's actually a lot less storage. Yeah? So that's a different way to kind of implicitly remember Q. Is the usual trick. OK. So I should be really careful to clarify that we've taken 2 algorithms, and they feel almost the same in terms of their output, but they actually aren't quite. So remember, we have Gram-Schmidt, which starts with A and post-multiplies by upper triangular square matrices to get to something whose columns are orthonormal. Right? Because remember, Gram-Schmidt's job is to take a set of vectors and orthonormalize them. Right? So Gram-Schmidt doesn't actually need those vectors to span all of Rm. Now we have this new algorithm, Householder, which takes A, pre-multiplies by a bunch of stuff until it's upper triangular. So it pre-multiplies by a bunch of square things. So do you see the difference? That Gram-Schmidt, R is guaranteed to be square. And in Householder, Q is guaranteed to be square. Right? So in particular, we have the following situation. Like Gram-Schmidt leads to a Q, which is M by N, and an R, which is N by N. And Householder leads to a Q, which is M by M, and an R, which is M by N. Right? So actually, the algorithms feel the same, but they're a little bit different. In fact, the book was a little sloppy about this, so that's what I edited in the chapter. Everybody understand that? No, there's a reasonable question, which is, can I kind of convert from one into the other? And the answer is going to be, of course, yes. Yeah? So let's think about how to do that. In particular, we'll think about the typical case here, which is least squares, where there's more rows than columns, and I'll let you think about the other case. Okay. So probably the more compact one. Which of these 2 cases is going to be the more favorable one for least squares? Gram-Schmidt, right? Because that's the one that has, because n is the small number here, right? So I prefer my square matrix to be the n by n one, yeah? But I'd like to use the stability of Householder. So I kind of want both, yeah? So let's see if I can get it. What do you think the answer is? Yeah. So in particular, if we think about Householder, what are we going to end up with? Well, we're going to end up with like this giant matrix Q, and we're going to end up with a matrix R, and which is like kind of tall and skinny, right? In particular, R has one little square here, which is upper triangular. And then what is this entire block? Zeros. Yeah. So an upper triangular non-square matrix is kind of a funny matrix. It's just a ton of zeros. Yeah. Okay. So again, remember that what are our dimensions here? So this is we've got n columns here, right? And this is m rows, like that. So here's what I'm going to do to Q. I'm going to take Q, I'm going to separate it into Q1 and Q2, like that, right? And I'm just going to do this by taking the first n columns and then the remainder, okay? Then here's the thing, in the product, so let's call this maybe R1 here. So really, what is QR? Well, if I do block matrix multiply, it's Q1 R1 times plus 0, right? So the reality is that what I can do, if I want to use an algorithm like Householder, but I want to get this, what we call maybe reduced size or compact QR factorization, is that I just don't remember the right chunk of Q. I only need the left part when I construct it. Does that make sense? Now, we have to be so careful when we do this. In particular, so let's say that Q is an m by n matrix. So Q is an R m by n, like that. So what do we know? Like if I did Gram-Schmidt, we know that the columns of Q are orthonormal, right? They're all unit length and they're all orthogonal. So in particular, what we showed is Q transpose Q is equal to the identity n by n, right? Now we often think like orthogonal matrix is square, in which case we also have that Q transpose is also the identity. But in this case, that is not true. So it only works in this setting. Okay? So that's where you have to be a little careful, right? And this includes on your homework. Yeah. So that's when you work with these reduced size QR factorization, you end up, at least for least squares problem, with a set of orthonormal vectors, but they don't span Rm. So like, so you can only get the first expression here. Does that make sense? Cool. All right. So anyway, that gives you, I'm sorry, I jumped the gun a little bit. That gives you the stability of Householder with the shape of Gram-Schmidt, which we want. Essentially, all we did was use this nice fact here to lead to our expression. Any questions? Fantastic. Well, by some miracle, we've actually made it to the end of QR factorization for the day. And now I think we are officially done with every possible way in the entire universe to solve least squares problems, at least ones that are dense. Yeah?
What did the runtime of this end up being?
Yeah. So it actually is still, it's let's see. It ends up being cubic. If you ask me in terms of m and n separately, I'd have to think about it. That's a good question. I'd have to go back and look at the steps, but it's easy enough to do.
Yeah.
I mean, when you multiply by the HB, that's a linear, actually, if you look at it. If you like unroll the product, and you're doing, yeah, get through. I don't know. I don't want to do this live because I'm going to get it wrong. But it's in the book, and I'm sure you can work it out. Cool. Great question. Sorry I can't answer it. All right, folks. So with that, if you haven't started your homework, please, for me, try running the starter code. That's all I ask. I mean, also to do your homework, but at least run your starter code and make sure it works on your laptop. Yes? You can't hurt to drag your mouse once the window pops up. Yeah. And if you've done that, then you've done probably the hardest part of the homework.
You also need to make sure the polyscope works and all
Yeah.
the packages.
Yeah.